ResNet is actually a recent model. It was introduced by He and al. In 2015. It won a Kaggle competition on ImageNet with an error of only 3.5%, and it has 152 layers. 152 layers is what we call a very deep network. Yeah? You compare with all the others here, like VGG 16 or VGG 19, we're talking about 16 layers or 19 layers. So 152 layers is deep. Yeah? And still, it works well on deep networks. Right? Now, usually, deep networks don't work that well. Why? Well, we have to suffer or to deal with vanishing or exploding gradients. And so before we're gonna go a bit deeper on ResNet, I will explain what vanishing and exploding gradients are. So let's start with vanishing gradients. And vanishing gradients are related to the fact that you would use sigmoid activation. Yeah? Remember that before the millennium, sigmoid was often used. Yeah? ReLU came after that. Yeah? And when sigmoid is used and you make a deep layer, you will run into the vanishing gradient problem. And let me explain what it means. Right? So here is a 3-neuron network where we have an input that I multiply with a weight W1, and here I have an activation A1. Here W2 activation A2, W3 activation A3, and then I have my prediction. That prediction I'm going to compare with the true value, and this will be in the form of a cost function. And then I'm going to take the derivative of that cost function to actually find the minimum of that cost function. Yeah? So remember, in gradient descent, these are your weights, this is your cost function, and the cost function, for example, in mean squared error was quadratic. And then you're basically gonna go downhill and find the minimum of that cost function. Now, we've seen that in deep networks, the way we will do this is backpropagation. Why do we use backpropagation? Well, because the activation A3 that generates the output is not dependent on W1 directly. Yeah? It is indirectly dependent on W1 if you actually work your way through. We've seen that in the video on backpropagation. So that means if I want to calculate the derivative of your cost function with respect to W1, which is this here, yeah, that I will need to take the derivative of my cost function with respect to A3. Yeah, cost function depends on A3, and A3 depends on A2. So that's A3 depends on A2 times A2 depends on A1, A2 depends on A1, and then A1 depends on W1. Yeah? So that gives me the relation between C and W1. Yeah? So I need to backpropagate and update my weights all the way to the input. Okay? Now, what is the problem with sigmoid? And I drew the sigmoid here. So this is Z. Yeah? And the red curve is our famous sigmoid curve that we see. Yeah? And it is 1 divided by 1 plus e to the minus Z, actually. Yeah? I wrote X, but it should be Z. Okay? And then what we need to do is we need to calculate these derivatives. Yeah? Remember, before the millennium, all these A's were sigmoid functions. And here in green, I have shown how the derivative of a sigmoid function looks like. Yeah? This is the formula. Just take that formula as given. Yeah, I'm not going to show you how you get there. But it's important you understand what the picture or the graph looks like. And this is the graph. So you have 0, then it moves up to 0.25, that's the maximum, and then it goes down to 0 again. So that means that all of these, yeah, these are all activation derivatives, will be between 0 and 0.25. This one as well, and this one as well. Yeah? So that means that, you know, you're multiplying always with 0.25. So that means that you become smaller and smaller and smaller. So the more nodes you add, the more times you're going to multiply with a number between 0 and 0.25. So at some point, this whole term here will be nearing 0. Yeah? So when this whole term is nearing 0, this term is nearing 0, and your new weight is the same as your old weight. So actually the algorithm has stopped, and this is not what you want. Alright? So this is the problem of vanishing gradient. Now, how can we solve that problem? Well, one way to do it is through ReLoop.